Let's move now to allocation methods. So basically, let's see how we can answer the question, how do we know where each file is? First way to go with this is to choose contiguous allocation. Is, as the name suggests, and it's similar to what we have discussed when we were talking about memory. So you put, in this case, one file after each other. And if you remove a file, like here, then you leave a hole that can be potentially reused later on by other files if they fit, of course. It's easy to implement. Each file needs to be associated basically with two numbers, the first and the last address, or the first address and the number of blocks. It's also good for performance if you are doing a single scan reading and you scan from the beginning to the end. This, of course, is true for rotating disks, in which close-by locations are faster to access than locations that are distant. If it's an SSD disk, it doesn't really matter that much. But you have fragmentation, okay? Exactly as you saw with contiguous allocation when we were discussing memory. And of course, you also need to know in advance the size of the file, which is not really realistic, meaning, especially because many files can have a size that changes over time. So even if you know the size when you want to store the file, what would you do if then the file changes size? It becomes larger than the number of blocks you actually have. Still, as always, there is no real good or real bad here. It really depends on the setup. Contiguous allocation is used when you keep stuff on compact disks and DVDs and so on. Why? Because there you only write once, you don't really modify the stuff, and you know the size of all the files you have to put, and those are not going to change. So as you can see, this can be used in practice. It depends a bit on the case, the support, what is the scenario you are taking into account. An alternative way to go, if you want to avoid this problem of fragmentation, is to use linked list allocation. So you use a portion of each block to point to the next block, and use a special number to refer to the last block. And then basically you can scatter around the blocks of a file into blocks in the disk that do not need to be contiguous. Okay, so you have the first block 0, which points to the first block address, which is 7 in the physical device, which points to the physical block number 2, and so on and so forth. Okay. Now you need to maintain only one number per file, which is the address of the first block. But on the other end, you don't know exactly where the block number n is, because now it's not contiguous. You cannot just sum n to the first one. You actually need to traverse all the blocks until you find block n. As you can imagine, this is not really practical, especially because if you have to traverse all the blocks every time to find where a specific block is, and all the blocks are on disk, and you have to do a lot of context switches to access the blocks on disk and so on. Probably this is not really the best in this type of setups. Also, you waste now a small amount of bytes inside the block, because now you need to store the pointer, so you cannot really use the entire block for your data. For putting content of the file, you need to keep part of it to maintain the pointer. It's not a big amount of, it's not a big portion of the block, but still focus on the fact that we always have this space and time trade-offs. Okay, so in this case, you pay space because you put it inside each block. You need to take a portion of that block to keep the pointer to the following one. You can optimize this, of course, and you can decide to load the information about where each block is and what is the next blocks in main memory instead of disk. And this is the file allocation table. Okay. So you can keep a list of all the physical blocks. You can keep track of the address at which each file starts, as you were doing with a normal linked list. And then you can just traverse this table in memory to find where each block is. It's still a sequential search. You need to go one by one until you find the block you want. But since you don't have to interact with the disk and you keep all this information in memory, then of course it becomes faster. Also, in this case, you need to pay a price, and again, it's complexity in space, because now you need to use part of your main memory too to keep track of this, and you need to load it when you boot up your operating system, so it takes a bit of longer time to boot up and so on. And here is just a simple example of how you can compute the size of this table based on the disk size and the block size and how many bytes each address in the file allocation table is taking. Okay, so this is the, you have here the plus and the minus, so the pros and cons that we just discussed. Final one, which is used in Unix, is to keep inodes. So basically to associate a small data structure to each file. This data structure contains the attributes of each file. You load it in memory only when you are trying to access the file. And this data structure, the node, also contains the initial, an initial set of addresses, let's say the first 8 blocks of the file, so that if you have to pick a specific block out of the first 8 blocks, you have the addresses in memory and they are pointing to the specific block on the disk. Of course, there is no guarantee that you need 8 blocks, and at the same time, there is no guarantee that 8 blocks are enough. If you don't need them, well, you are wasting some of them, but that's not a big deal. But if you need more, of course, you need a mechanism to find out also where the other addresses are. And you can do this keeping an extra address to a block on the disk, but this is a special block that is only used to store the address of the following blocks. Sorry. And you can do this with different levels of indirections. So this is level 1, you have a pointer to a block that contains addresses. You can have a pointer to a block that contains pointers to other blocks that are full of addresses, and you can go up to 3 levels of indirection. I will show you an example of this in the exercise session. Now, if you only load inodes for the files you actually open, they take less memory. You need to maintain a smaller amount of information in memory about the files that are open. And it's also proportional actually to the number of files that you have open. But it becomes complicated again when you have very large files because of these mechanisms of pointing to a block that contains pointers and so on. So you need, it works well as long as the majority of files have take a number of blocks that is more or less covered by the ones that are already made available directly in the inode.